Hello everyone, my name is Vít Růžička and I will be talking about our paper Deep Active Learning in Remote Sensing for Data Efficient Change Detection. So the task of our paper is the change detection between two co-registered images. So let's say we have images from 2012 and then images from 2015, and we want to find predict the changes inside these two images. The problem we are facing with is that we have a large dataset with a highly unbalanced class distribution. So you can imagine that if we were to tile this image into individual patches, the number of patches which would contain any relevant change would be much smaller than the number of patches which do not contain any change. And so namely in our dataset, this is 1 to 83 ratio. And so our goal is to lower the annotation effort because we believe it's possible not to have to go through the whole 84,000 images, but to select some subset which would be more important. So the approach we are taking is the active learning algorithm. There we start with a small annotated training dataset. We train a simple model on this training dataset, and then using the learned representation of this model, we want to somehow select the additional samples to be added into the training dataset. And so the key idea is to add samples with high uncertainty score to improve the model where it is being uncertain. And for that, we are using some sort of acquisition function which goes through the whole unlabeled dataset, selects samples which have high uncertainty score, and then asks the user to provide labels for the selected samples. And then finally, we will add these new samples into the training dataset and then continue with the next iteration of the active learning algorithm. So we need to look into the detail of the model design. We are using a Siamese network for change detection. So this means that we have two encoder heads which share weights, and they are encoding images from these two from this pair, and then the feature representation is being concatenated together and then propagated throughout the model. We are also using the UNet model architectures as an inspiration, and so we have these skip connections which allow us to preserve details throughout this model. And then finally, we are using a pre-trained ResNet34 inside the shared encoder head as a starting point. And so namely these two last points allow us to be able to train this model and have some sort of meaningful representation being learned even from a very small training dataset, which is in particular very important in the active learning scenario, where in the early iterations we do not have much training data. For uncertainty estimation in deep learning models, we are using two paths. One of these is to use explicit ensembles of models, which basically means training multiple models, and then from each of these models which have been trained on the same training dataset, predict different predictions for one sample. And so then working with these predictions, we can average them and then use some metrics to estimate the uncertainty. This standard approach is in theory slow because it needs to be training multiple models, and so we are also testing the implicit ensembles, where instead of training multiple models, we train a single model and then use the stochasticity of the regularization processes to simulate multiple forward passes. And so the technique we are using is called the Monte Carlo batch normalization, where we use batch normalization in training mode during inference. And so with both of these methods, we are able to arrive at predicting multiple different predictions for each single data sample in our dataset, in the unlabeled dataset. And so for each of these samples, we are able to then use some metrics of variance or entropy of the predicted posteriors, and then summing across all the pixels to get a single score to evaluate these samples. And so this will guide us to select only the most uncertain samples in the dataset. So we are testing the model ensemble and the Monte Carlo batch normalization methods with two baselines. The upper baseline is a comparison with a model which had access to the whole fully annotated dataset, where we selected all the changed patches in that dataset and then added a matching number of unchanged patches. As a lower bound, we are using a baseline where we have replaced the acquisition function from one of these methods to be a uniform random sampling. So let's look at the results. These two are the random baselines. This line corresponds to the full dataset baseline, and all of these are our tested methods. And so you can see with the progressive number of samples in the training dataset, the performance is increasing. And in about 850 samples, all of these tested methods are able to reach the same performance as the full dataset baseline, with only a fraction of the data, so roughly 1% of the data being labeled. We can also see that the ensemble method is slightly outperforming the Monte Carlo batch normalization in the early iterations. However, that both of these methods are able to catch up. And also you can see that the random baselines are doing very poorly. And to provide some sort of intuition behind it, we can look at the next slide. So here we have a visualization of the number of sampled or edit samples from the changed and not changed category. So the patches which contain change and the patches that do not contain any change. And we can see that both of these tested methods, the ensemble and the model ensembles and the Monte Carlo batch normalization, actually tends to automatically balance the acquisition of uncertain samples from both changed and unchanged patches. And so just as a note, this is being done without the access to the label information. This is being done purely through the uncertainty metric. And in comparison, we show the random baseline approach, where basically it is matching the original ratio in the original dataset between these two classes, which was 1 to 83. And so the added samples are not really representative of what we would like to add. So in conclusion, in our paper, we have designed a Siamese UNet model with a pre-trained ResNet34 encoder with the specific requirements of active learning in mind. Both of the tested methods match the same performance as a baseline approach which had access to the whole labeled dataset with only a fraction of the labeling effort, so only 1% of the data. We also demonstrate some intuition behind the process, and we show that the active sample selection tends to automatically balance the training set, despite the extremely imbalanced nature of the input data. And then also we show that the standard approach of explicit ensembles improved slightly faster in the early iterations, but that the novel Monte Carlo batch normalization method is able to catch up in the later iteration. Lastly, for future work, we would like to propose exploring faster ways to quantify uncertainty to reduce the time bottleneck of active learning research. So as a bonus slide, we are also providing some active learning timing information, as was asked by the reviewers. In particular, we are looking into the training and acquisition steps of the active learning algorithm. In isolation, we can see that the Monte Carlo batch normalization method is doing on average 61% faster during the training step, regardless of the training set size. However, that it is on average 35% slower during the acquisition step. And we believe that this is due to the fact that we are running in an unoptimized training mode, and we have to fix the prediction batch size to match the training batch size. Nonetheless, when this is put together, the whole run evaluation, the Monte Carlo batch normalization method soon overtakes the ensemble method in performance, and namely in the last iteration, it's roughly 32% faster. This is everything on the presentation, so thank you very much for your attention. If there are any details you would like to know, you are free to read the paper, and if you have any questions, please feel free to ask. We will be very happy to answer them here as well.